Hi, my name is Harm van Seijen. I'm a researcher with Maluba. So Maluba is a company situated in Montreal. And so they've been acquired beginning of this year by Microsoft. So we're now officially part of Microsoft Research. And by the way, I'm now in Japan. Maybe you can see it in the background, but usually I'm in Montreal. So today I'm going to talk about some of the work we've done on the game Miss Pac-Man. So we were actually able to achieve the maximum possible score on this game, 999,990 points in total. So I'm going to talk about the main strategy that we used to achieve this score. So let's start the presentation. All right, I hope you can all can see this. So this is joint work with Mehdi Fatemi, Josh Romoff, and Romain Laroche. So I want to start by giving some context. So in 2015, DeepMind came out with a Nature paper on DQN, which is a deep reinforcement learning method that was able to achieve above human performance on a large number of Atari games. And since then, a lot of new methods came out, variations of DQN that achieved an even higher score. But up to today, there remain a number of games on which these deep reinforcement learning methods perform very poorly on. And so it's an interesting question to ask, what makes a game hard from a machine learning perspective? What makes it hard from a reinforcement learning perspective? So we have a pretty good idea. So one important aspect is the task horizon. So games with a long horizon, if a game has a long horizon, then a player needs to look very far into the future to determine what is the best action for the current time steps. So those games are typically called planning games. And examples are Monsoon's Revenge, game you see below there. On the other hand, you have games with a short horizon. And for those kind of games, you don't have to look very far into the future to determine the best actions. And examples are Breakout and Space Invaders. And such games are typically called reactive games. Now, long horizons are not the only aspect that makes the games hard. Some other aspects are partial observability, are games that are hard to explore. So partial observability means that I just hear that my slides are not moving, so I'm just going to try to change that. So so this kind of so task horizon was one of the aspects that can make a game hard. But there are other aspects that determine whether a game is hard or not. So these are whether it has a long horizon, whether it's partial observable or difficult to explore. So like I was saying, a game is partial observable if an agent needs to remember things from the past. So just looking at the current game screen is not enough in order to determine what the best action is. It has to remember things from the past. And a game is hard to explore if, for example, rewards are very sparse or if an agent dies very quickly. So these are some well-known aspects that can make a game hard. So now let's have a look at the game Miss Pac-Man. So Miss Pac-Man is a game from 1982. It's an Atari 2600 game as well. And the goal is basically to eat pellets. So these are the little dots on the screen. And to eat as many of those pellets as possible while avoiding the ghost. So if you eat all the pellets on the screen, you move to the next screen, to the next level. And if you touch a ghost, then you lose a life. So that's the basic concept of the game. Now, so Miss Pac-Man is one of the hard Atari games, and you can see that in the table on the right side. So the table shows the performance of several deep reinforcement learning methods, as well as the human baseline. So the human baseline gets around 15,000 points, And all these deep reinforcement learning methods, they do much worse than that. So, and it's to be clear, so the human baseline is the baseline provided by DeepMind. So it's just an average player. So it's not the best human player. So the high score on Miss Pac-Man is actually 250,000, around 250,000 points. So it's much higher than that. So this is really an average Joe baseline. And those deep RL methods, they do much worse than that. So now what is interesting about this game is if you look at those different reasons why games can be hard, and they don't really seem to apply to Miss Pac-Man. So it doesn't really have a long horizon. It's not partially observable. You can see the full screen. You can see everything. And it's also not particularly hard to explore. So this raises the question, what makes Miss Pac-Man a hard game? Why do these deep RL methods struggle so much with this particular game? Now, I'm going to come back to this question later, but before I'm going to go there, I want to introduce some basic concepts of reinforcement learning. So in reinforcement learning, the goal is to learn behavior by interacting with the environment, with the world, with the environment. And so what you can see here is that, hopefully you can see this here, it's a basic reinforcement learning model. So you have an environment and you have an agent. And the agent takes actions at discrete time step in this environment, and the environment responds with an update of its state as well as a reward. Now, the goal of the agent is to find the behavior policy that maximizes the sum of rewards received over time. So that is the goal of the agent. And more formally, we can define a reinforcement learning process as a markov decision process, which consists of a set of states, X, A, a set of action, P, the transition probability function, R, the reward function, and gamma, the discount factor, which specifies how future rewards are counted with respect to immediate rewards. Furthermore, we can define a policy pi. This is a function that gives the selection probability for each action conditioned on the state. And a very important term is the return. So the return is the discounted sum of rewards. So, and it's the return, the expected return that an agent has to optimize. So furthermore, for each policy pi, we can define two value functions. So, and these value functions play a very important role with finding a solution to an MVP problem. So, we're trying to find an optimal policy. And so there's two value functions. So, the state value function gives the expected return conditioned on the state. So it means that if you're in a particular state X and you follow policy pi, so you take actions according to policy pi, what is the expected return? That is what the state value function gives. The action value function gives the expected return conditioned on the state action pair. So it says, if I'm currently in state X and then take action A, and after that I follow policy pi, what is my expected return? So these are two very important functions in trying to find an optimal solution. And so finally, I want to define, well, there's two types of tasks you can consider when you have an MVP. The first one, the simplest one, is an evaluation task, which means you're simply trying to estimate those value functions for a particular policy pi. And the main task is the control task, which means that you try to find the optimal policy, which we indicate by pi star, of a particular MVP. And that's the main task that we want to solve. Okay, so now that I have these basic concepts defined, I can come back to the question, why Miss Pac-Man is such a hard game? And our claim is that this has to do with the complexity of the optimal value function. To explain what I mean by that, I consider a function f, which is a mapping from x to the real values. And for the sake of argument, let's assume that x is a finite, a huge set. Say it has a size of 10 to the power of 100. Now our goal is to learn an approximation f hat from samples such that the difference between f hat and f is smaller than some epsilon, than some epsilon, so some small value. So the question now is, how hard is this task? And more importantly, what aspects determine how hard this task is? Now, if we wouldn't use function approximation, then it would actually be the size of X, the size of the set, that would determine how hard this is. And in this particular case, it's a huge set, so it's a really hard and pretty much an impossible problem. But if we use function approximation, the size of X doesn't really matter anymore. It's something else. So what matters is how easy is it to generalize for a particular function. And to show you two extreme examples, here are two extreme examples. So one example is if f is a linear function. So this is a case where it's extremely easy to generalize. So in fact, you only need two samples to get a perfect approximation of f. On the other hand, if f consists of random numbers and there is no correlation whatsoever between subsequent samples, then it's really hard to generalize. And so then you would need, at that point, the size of x starts to matter again, because that's the number of samples you're going to need to get a good approximation of f. So what I mean by a complex function is really, it's a function that is for which it's really hard to generalize. So a function that requires an enormous number of samples to accurately estimate. So the question to ask now is, do these complex optimal value functions occur in practice? Because, of course, the real world is not random. It contains a lot of structure. And more generally, you can make the argument if a human quickly learns to do well on a task, this means that the optimal value function of this task is not complex. And of course, this is the case for the Atari games. All these games, they have to be fun to play, so it's not extremely hard to get a decent score on these games. So you can use this argument and say, okay, these complex optimal value functions, they don't occur for those Atari games. However, it's an invalid argument. And the reason for that is that, first of all, humans don't aim for optimality. And second of all, behaving well can be a lot easier than behaving optimally. And so this is a very important point to realize. So all these deep reinforcement learning methods, they aim for the optimal policy. And the reason is that they evolved basically from tabular methods, and in the tabular world, problems are really simple, and it makes sense to talk about optimality and trying to find an optimal policy. However, you can ask yourself whether that's still a good policy if the problems become more complex. Because humans, which are the pinnacle of intelligence, and are able to deal with extremely complex environments, they clearly don't behave optimally, or they don't even aim to behave optimally. So it's a valid question to ask whether our AI methods should aim for optimality when dealing with these really, really hard and complex environments. So to show you an example of a task for which it's, hard to do optimal on, but easy to do well on, you consider the task shown here. So an agent has to eat a number of different foods as quickly as possible. Now, this task, if you want to do optimal on it, it's really hard, because it's actually an instance of a traveling salesman problem, which is known to be incomplete. This means that if you have a large number of foods, it's going to take a long time. It's going to be very hard to find the optimal policy. At the same time, it's really easy to do well on this task. If you always simply move toward the closest food, you're going to end up with a policy that gets a really decent performance and is very easy to learn. But it's not optimal. So this basically shows two things. So first of all, yes, these complex optimal value functions can occur in practice, can occur for Atari games. And second of all, it outlines a strategy to deal with them, which is, just like humans, let's not aim for optimality, but aim for something that is good enough but easy to learn. So to formalize this idea of aiming for something that is good enough, I want to introduce, I want to make a distinction between two terms. The first term is the performance objective, which specifies the goal, and this is determined by a reward function and a discount factor. And the second term is the learning objective, which specifies a feedback signal. And this is also determined by a reward function and a discount factor, but can be a different reward function and a different discount factor. Typically in reinforcement learning, this separation is not made. You just have a single reward function which acts both as the performance objective as well as the learning objective. But it's been known for some time that having a single function for this is not always a good idea. So for example, with research in intrinsic motivation, which consists of adding an additional reward function to the reward function from the environment in order to speed learning. So, with this distinction, I want to take things a step further by considering two completely different reward functions. So, two other terms I want to define is consistent learning objective. So, you have a consistent learning objective if the greedy policy with respect to the value function is optimal with respect to the performance objective. The second term is a relaxed version of that, which I'm going to call a semi-consistent learning objective. So you have a semi-consistent learning objective if the greedy policy with respect to the value function does well with respect to the performance objective, but not necessarily optimal. So with these terms defined, I can now very concisely define our goal, which is if we're having these complex optimal value functions, what we want to do is we want to find a learning objective that is semi-consistent as well as easy to learn. Now, finding such a learning objective in the general case is very hard to do, but I don't have a complete answer of how to find such a learning objective, but it can give an incomplete answer, like a partial answer, because what it can give is a somewhat general strategy to achieve this. So it's a somewhat general strategy because it doesn't always work, but it works for some domains. It works very well, and this Pac-Man is one of those domains. So it consists of the first step is as learning objective to use the p-value of the uniformly random policy. So you still use the same reward function as the performance objective, but instead of trying to behave optimally with respect to it, you simply evaluate the random policy. And the second step is to use reward decomposition to learn those p-values, because that can be a really efficient way to learn those p-values. Sorry, I have a bit of a problem with that. So the surprising thing about the strategy is really that this leads to a semi-consistent learning objective. Because if you simply use the p-values of the random policy, you would expect this not to work at all, not to lead to a good policy at all. But it actually, in some cases, can do very, very well. And that's really the most surprising part about the strategy. So in the next few slides, I want to show two things. First, I want to show why, in some cases, acting greedily with respect to the random policy can give you a really good performance. And like I say, it's a somewhat general strategy because it doesn't always work. So I'm going to show you a positive example as well as a negative example. And after that, I'm going to show how you can use reward decomposition to learn that q-value function very efficiently. So first, I'm going to start with a positive example of acting greedily with respect to the random policy. So the task I consider is a very simple navigation task. So we just have an agent that has to move towards the goal state. 4 actions: up, down, left, and right. And deterministic transitions. And there's a +1 reward for reaching goal state and 0 reward otherwise. And the discount factor is 0.9. Now, if you look at the Q values, if you look at the state values of the random policy, then it's going to look something like this. So red means that state has a higher value. So it has this particular shape because states that are close to the goal state, it takes less long under the random policy to go from that particular state towards the goal state. So the shape of the value function of the random policy, it's like a hill shape with the goal state located at the peak of the hill. So if with respect to that value function, then what happens is that you're going to climb upon the hill, so you're going to do hill climbing and move towards the goal state. So this is actually an example where acting greedily with respect to the random policy will actually give you an optimal policy. So in this particular case, it's actually a consistent learning objective. So this is really surprising because you're finding the optimal policy by simply solving an evaluation task rather than a control task. And solving an evaluation task is a lot simpler. You can do all kinds of tricks to speed up learning, and reward decomposition is one of those tricks. So now the negative example. So if I change the example a little bit, such that I now have a bridge in the middle, so the agent has to cross a bridge before it can reach the goal state, and there is a negative reward associated with falling off the bridge. So under the random policy, the states on the bridge have a really negative value, because under the random policy, the chance of falling off the bridge is very high. So if you would act greedily with respect to the Q values of the random policy, then the agent would never come close to the bridge. So in this case, the agent would never reach the goal state. So this is an example, a very negative example where that approach doesn't work. But like I said, in some domains it works very well, and if it works, it's very powerful because you can use all kinds of tricks. So onto reward decomposition. So this is one of the tricks you can use to speed learning if you're dealing with an evaluation task. So assume that the goal is to learn the Q values of the uniform random policy, pi bar, given the environment reward R environment. Now, first step of reward decomposition consists of simply decomposing the reward function into several component reward functions. Say you decompose it into n component reward functions. In the second step, you assign a RL agent to each of those component reward functions. And in the third step, you compute for each component reward function the Q values belonging to the uniformly random policy. And then in the final, so after step 3, you have given that you have n components, you end up with n different q-value functions. And in the last step, you add those q-value functions back together into a single q-value function, which I'm going to call QHRA. And HRA stands for Hybrid Reward Architecture. That's the name we use for this whole approach. So, and you can easily show that QHRA is equal to Q environment, which is the Q values of the random policy with respect to your environment reward function, which is the one that you're after. So this is a strategy to do reward decomposition, but so the main question I haven't addressed yet, which is why would this be a good approach to learn such a Q-value function? And I want to address that question with an example. So let's go back to this fruit collection example that I showed before. So you have an agent that has to eat a number of different fruits. But now instead of saying that it has to do it as quickly as possible, I'm just simply saying, okay, it just has to, I'm going to define my reward function as a +1 reward for collecting each apple, 0 reward otherwise, and the discount factor is some value smaller than 1. Now, if you look at the value function, then it's determined by 4 state variables in this case. So it's the position of the robot and the position of the 3 apples. Now, a decomposition I can make is as follows. So my first reward function gives a +1 reward for only collecting apple 1, but 0 reward otherwise. So if apple 2 or apple 3 is collected, there is no reward. And the second reward function gives a +1 reward only for collecting apple 2, and the third reward function gives a +1 reward only for collecting apple 3. Now, clearly, if you add these 3 functions back together, you get the original environment reward function again, which gives a +1 reward for each apple. But if you look now at the value function associated to each of those component reward functions, then it only depends on a subset of state variables. So in the case of the first reward function, it depends only on the robot and the position of the apple, of apple 1. So because it only depends on a subset of reward functions, those value functions are much smoother. They're less complex, so to speak, and they are typically much easier to learn. So what you gain by doing this reward composition is that rather than having to learn one very complex optimal value function, you're now solving many much simpler, much smoother value functions. And you can learn all those value functions in parallel from the same experience sequence. So it turns out to be an extremely efficient process. So that's the advantage of reward decomposition. And this is the main strategy we use to get this good score on the Pac-Man. So more specifically, so we have 2 steps. So to achieve a semi-consistent learning objective for the Pac-Man. So in the first step, we do some basic reward shaping. So this is just an intrinsic motivation technique to kind of pre-smooth value function. The main thing we did there is to give a negative reward of -1,000 for dying, for when Miss Pac-Man loses a life. And this was an essential step to make the reward decomposition possible. So in the second step, we learned the Q values of the random policy with reward decomposition. And the decomposition, we made a very basic decomposition, which is that we assigned 1 reward function for each object, so each of the palette, each of the ghosts, and each of those objects got this separate RL agent. And by doing that, we ended up with a total of 163 reward functions in total. And I just want to show a small demo now of how that looks like in practice. I hope that the video, you can see the video well. So I'm just going to play it now. So this is kind of a visualization of all those different agents. So, like I said, each object on the screen there's an agent associated with it, and the arrows kind of visualize the Q values. So each agent would like Miss Pac-Man to take a different action, basically, and the final action is constructed from a weighted average of all those individual agents. So this kind of this illustrates nicely how these different functions work together, how these different agents work together. So now let's have a look at some of the results. So here you see, our main results. So the blue graph shows our method, HRA, hybrid reward architecture, and its baseline we used a popular deep learning method called A3C. We have two versions of that, and they correspond with different preprocessing. So the red line is like the standard preprocessing, and the green line is more advanced preprocessing. But yeah, it doesn't make much difference for A3C basically. But so what you can see is that HRA gets a score of around 25,000. So which is way below the human baseline of around 15,000. So it's a really good score. And in the final experiments, we added something extra. We added executive memory. This means that you memorize for each level the zero kill trajectories. So what this basically means is that you play each level a number of times, and if you got zero kills, you record that trajectory and reuse it the next time you see that same level. And it kind of exploits the fact that Atari games are ultimately deterministic, so there is not real stochasticity. It's always, it's if you use the same actions, you end up with the same result. Now, so it's kind of a trick, but it's only a trick that can improve methods that are already very strong. So if you use the same trick, apply the same trick to A3C, for example, it wouldn't make any difference because A3C never gets past level 1. So you need an already strong method to see any difference. So what you see here, so with these results, when we add this executive memory, we were able to very efficiently go to 1 million points, or actually 999,990, and you can't get a higher score because after that the score resets to 0 again. So there's two interesting things about this curve. The first one is how efficiently it gets there. It's 3,000 episodes. So compared to the previous graph, which took like 5,000 episodes. And the second one is the shape of the curve. So it starts off with a very with a low slope. The slope is not very steep. And that is because it has to learn its policy, it has to learn how to navigate the maze, it has to learn how to avoid ghosts and all those kind of things. And once it learned that around 2,000 points, then it gets this very steep slope, and it very efficiently gets more and more points. So these are our main results. And so just to summarize, so our main strategy is really to, just like humans, not really go for optimality, but just aim for something that performs well. And that, but that is very easy to learn. And that worked very well in this case. So this is the end of my talk. So I'm going to answer some questions now, if you have questions. So I'm going to stop sharing my screen and see if there are any questions. I think for R2, the relevant state variables should be Apple II and not 1, right? Let's just quickly have a look. Could be a typo. Oh, yeah, that's right. Sorry, that's a typo indeed. Yeah, so the relevant state variable is Apple II indeed. Good catch. How generalizable is the strategy to other tasks? So that's a very good question. So like I said, the main strategy relies on acting greedily with respect to the random policy. Now, so that doesn't work in all domains, but it works on some domains, and it works on some really hard domains. So we're currently working on research to look more carefully on what domains it works and on what domains it doesn't work, so that you can say beforehand already, okay, this is a domain that it works on, and this is a domain that it doesn't work on. So if you talk about that particular technique, yeah, that only works doesn't work for all domains. It only works for a subset of domains. But if you look at like even a step higher, if you go if you look at the strategy of simply trying to aim to separate the performance objective from the learning objective and not aim for optimality, but more like humans, try to aim for something that is good enough, I think that is a very general strategy that can be applied, well, much more broadly. So there are a number of different ideas, and like some of them are more specific and can be applied to a more only a subset, but some of the more deeper underlying ideas, I think those are very general and can be used as a more general research direction. Has HRA been used for any other games? So we were really focused on Miss Pac-Man for the reason that I mentioned, that all these usual suspects, the usual reasons why games are hard, they didn't apply. So up to now, we really wanted to understand that and come up with well, mainly understand it, but we were also able to come up with a strategy that could actually deal with the challenge, the particular challenge. So yeah, the short answer is right now we only applied it to Miss Pac-Man, but we're looking into other games as well. What's next for your team? Yeah, so in general, our team focuses on fundamental challenges. So trying to understand what makes RL problems hard and how to deal with that. So we're really focused on like all the fundamental challenges, things like partial observability, things like exploration. So we're not focused on first of all, we're not focused. We're not just trying to solve games or something. We're interested in more in the fundamental challenges, trying to understand what makes RL problems hard and how to deal with it. And we're looking at any domain that can help us with that question. So we're looking at things like exploration, generalization, different kind of things. Can you use HRA to bootstrap a policy and then migrate to a less restrictive queue function? So that's a good remark. So you can, I mean, it's definitely that could be a strategy to just use HRA to get like an initially good policy and then try to use that to try to get an even better policy. But so it kind of goes against the idea, though, of the more deeper idea of should you aim for optimality? If you want to make methods that work in the real world, which is extremely complex, and you know you can only observe a really small part of that. Like I think the more interesting question is, do you want to aim for optimality? Is that really something you want to go for? Is that even realistic in the real world, where you have so many unknown things? And I think maybe that's the more interesting question. It's not so much could you use it to get a even better policy, but is that really what you want to go for? And I think if you really are interested in building real world applications, then maybe the answer is maybe you don't want to go for optimal policies, but maybe just trying to go like the method we use, trying to go for something that is good enough, but it's very easy to learn. Maybe that's a more interesting route. How does it compare to policy gradient approach? Well, so A to C is a policy gradient approach. So when they talk about state-of-the-art methods, w.r.t methods, we looked at policy gradient as well as value function based, value-based approach. So A to C is policy gradient. Could you name any other applications of these techniques in any other field in the software industry? So, like I said, so our team is really focused on the fundamental research. So we're more looking at what are the obstacles that are in the way of keeping RL from applying RL to really big problems, and working on really general methods that can be applied in many different settings. And so I haven't really looked at specifically at problems in the software industry that we could apply it to. But yeah, if you have any suggestions, please send me a suggestion. Perhaps maybe I can learn something from that. Did you apply CNNs to understand every view with Q values arrows? No, we didn't apply CNNs to understand a view. So, so the way those arrows were generated, so we did the decomposition based on those objects. So, and we simply map the Q values of an agent associated to an object to that particular object. So it's just a visualization trick. So we didn't use CNNs for that. If IBM rebuilt Deep Blue today, do you think they would be using deep reinforcement learning? Oh, that's an interesting one. They didn't really need it, right? To beat the chess master. So. So they, if you don't really need it, you can go without it, and then that's fine, of course. In Go, they really needed it; they really relied on it. So yeah, so I don't know if they like. I don't know if you could get an even better score with Deep Blue if you apply deep reinforcement learning. I mean, they've done pretty well already without using it. I'm sure they would look into it and see if it could improve something, and maybe it would improve. Maybe it would improve performance even further. It would be interesting. Would be an interesting experiment actually, but I'm not sure if they're looking into that right now. I think the goal is just to look at harder and harder problems, and chess is sort of considered solved now. Go is solved as well, so it's on to the next thing. I think that's the more interesting thing to look at. Thank you very much for listening, and good to have fun with the other talks, I would say. Bye.